Hello, everyone. In this lesson, I'm going to talk about only to find local max, local min, whether we use first derivative test or second derivative test, or cases that we can use either or both, okay? And or some cases that we can only use, one test and you cannot use the other. Okay, so we start with this example that where I saw some discussions in the Pronto app. So this function is from your homework. So f of x equals x squared over x minus 1. And we know the first thing we do is that we make sure we know the domain. The domain, of course, here is x not equals to 1. And from first order derivative, right? From first order derivative, we got x squared minus 2x over x minus 2 squared. And if we factor the top, we're going to get x times x minus 2. And the denominator, of course, is x minus 1 squared. Okay, so the domain for the derivative, once again, is actually the same as the derivative of the function itself. So in terms of critical numbers, we don't have the category that, the critical numbers is in the domain of function, but not in the domain of the derivative. The two domains are the same. So to find critical numbers, we said the first order derivative equals to, we said the first order derivative equals to 0. And as a result, denominator cannot be 0, numerator must be 0. So we get a critical number x equals to 0, x equals to 2. So we got a critical numbers. Critical numbers are 0, 2. But don't forget, right? These two critical numbers, they are both in the domain, so they make the first order derivative equal to 0. So as we understand, noted, right? Which is you don't need to write this in your work, actually. It's just for our information. The derivative of first order derivative at 0 is 0. And first order derivative at 2 is 0. Okay, so it's just to reiterate that 0 and 2 are critical numbers. Okay, suppose we do second derivative test. Okay, suppose we do second derivative test. Okay, derivative test. We can, right? Because you see the second derivative, after we find the derivative, the second derivative still has the same domain. And the function is differentiable, second order derivative is differentiable, first order derivative is differentiable. So we are going to use second derivative test. Okay, so let's test these two numbers, right? So we have these two satisfy second derivative test, right? So we got two critical numbers, and then we're going to plug in second order derivative, right? Second order derivative right here, right? That's second order derivative, and we're going to plug in the two numbers, okay? So plug in 0, and this will be 0. And the denominator to the power 3, and it's a negative 1 to the power 3, so this is less than 0. So according to second derivative test, critical number, second derivative test, second derivative at the critical number 0 is negative. That means it's a concave down. So we have a local, sorry. That was 0, sorry. Wait, what am I doing here? Okay. And let me just rewrite it, okay? Second derivative at 0. So this is a local max, okay? Local max at 0. Okay, local max at 0. And what is the value? The value of local max, we are going to have to bring this 0, the critical number 0, into the original function. That's going to be 0, 0, of course, the local max at 0, the where, and the what. Okay, so local maximum is 0. The second one, second order derivative at 2. Okay, so this is going to be 2. 2 minus 1 is positive. Positive raised to the power of 3 is positive, so this is greater than 0. Okay, so by second derivative test, we have a local what? Local minimum at 2. At 2. And what is the value? We're going to go back to the function and plug in the value 2. Okay, 2, 2. That's going to be 4. All right. Then you may wonder, how come the local max value is smaller than the local minimum value? Why is that? Isn't that interesting? Isn't that interesting? Well, for this question, we're done. But to see why this happens, you can look at the graph. Okay, you can look at the graph. This happens a lot. Because it's a local max, local min. Okay, so we have, I think this picture is not that complete. Okay, this picture is not that complete. Well, this software is okay, there we go. Okay, so we have two pieces. Okay, so let me make, this is -10. Well, -5 is okay. And this could be 10. Okay, so you can, now you understand why there's this local max and local min. Wait, no, it's this line. And alignment. Okay, you can see the local max. Local max is here. Okay, so in a neighborhood, so let me mark the local max. Local max is 0, 0. Okay, we make it a red dot. And local min is 2, 4. Okay, so these are, so recall the definition of local max, local min, right? It's just in a neighborhood, in a small neighborhood. Okay, in a small neighborhood that, we have, it is the highest, right? That's a local max. Local min in a small neighborhood, it is the lowest, right? So it's in different neighborhood. Okay. All right. So that was the use of first derivative test. So what if we do it by second? No, wait, sorry. We just did the second derivative test, right? We just used second derivative test. So now let's do first derivative test. The first derivative test, we don't need second derivative. So we're going to copy the whole thing so we don't have to do it again, right? So we're going to do second derivative test for the same question. Okay, first derivative test. We're going to use the first derivative test. first derivative test, we need to basically know the sign changes, right? The sign changes. So we need to discuss the sign changes of the first derivative. Okay, first derivative here. And we can just clean up all of these, right? Denominator is always positive. The numerator is a product of x times x minus 2. And using the same methods, using the same method I showed in class, or use whatever method you feel comfortable, okay? And we first determine the sign of x. The sign of x, of course, that's pretty straightforward, right? The sign of x changes sign as 0. X changes sign as 0. And when x is less than 0, of course, those are negative. At 0 is 0. That means it's a critical number. Beyond 0 is positive. X minus 2, the sign of x minus 2. The sign of x minus 2 comes next. Sign of x minus 2 is that we have number 9 once again. So relative to 0, 2 should be somewhere here. Okay. And for x less than 2, x minus 2 is going to be negative. At 2 is going to be 0. That means it's a critical number. And above 2 is going to be positive. Right? So now the sign of first order derivative, right? So the sign of the first order derivative will be apparent. All right, so we got 0 here, we got them lined up. We got 2, we got it lined up. And when we pick a number less than 0, we got let me just make sure everybody following me. Okay. When it's less than 0, right? Negative times negative, that's positive. Okay, so that's going to be positive. And then in the middle, here is positive times negative is negative. And above 2 is going to be positive. So by this time, we know the sign, we know the function, so we know the interval. But because it's not asking for interval of increasing or decreasing, so we don't have to talk about it. We just need to use first derivative test, right? So by first derivative test, okay, we will say f prime changes from positive to negative, change from positive to negative at 0, right? From positive to negative at 0. So we have, so f has a local max at 0. And of course, f of 0 equals to 0, right? And similarly, we say f prime changes from negative to positive right? So this is a negative to positive at 2. So f has a local minimum at 2, has a local minimum at 2, which is f of 2 equals to 4. So that's how you would do first derivative test. But in this case, you can do either method works. Okay, either method works. All right. So let's see. Let's do another example. Okay, let's do another example. This one is from our homework. This one from our homework. And the homework is asking us to do example number 2, to do both tests. Okay. But let's go over this question. Let's go over this question. Okay. First, we need to determine the domain. Okay, domain is x greater than or equals to 0. X greater than or equal to 0. Okay, because we have a square root and a fourth root. Okay, square root and fourth root. And let's take a derivative. I think I did something earlier. Okay, so here we go. We got that. So I'm just going to bring this over. First order derivative. First order derivative. Okay, we rewrite it. We rewrite it. Let's see, did I take a derivative? Never mind, we're just going to do this all over again, okay? First order derivative of x raised to the power half. We get a 1 over 2 x raised to the power of negative half. Whoops, negative half. Okay, sorry. Minus a quarter x raised to the power of negative 3/4. Okay, so by this time, actually, we can assess the domain already. This domain is going to be different from the function itself because this domain is going to be x greater than 0. So that makes 0 a critical number. Okay, so we should make a mental note. Okay, this already tells us 0 is one of the critical numbers. Critical numbers. Okay, so don't forget that. We're gonna we take a mental note and I just wrote it down. And next, of course, we're gonna set the first order derivative equal to 0 to find, maybe there's some other critical numbers, right? Here we go. So how are we gonna reduce this? How are we gonna reduce this? Okay, the general rule of thumb is to factor out the base with the lowest power. This one has the lowest power. Okay, so we're gonna try to factor this piece out. But in this part, we don't have it, right? We don't have it. So how do we create one? There are a couple ways we can create it, right? So see, for example, here you can see this as 4 under 2. 4 under 2. So we just need to multiply x raised to the power of negative 1/4, right? This will make it to be x raised to the power of negative 3/2. But this will make our expression off balance. So we have to multiply x raised to the power of positive 1/4. So this is another way to do it, okay? I noticed some of you did it this way. That's great. That's great. Okay, so by this time, we can combine these two because they have the same base. We just add up the exponents. Add up the exponent, so this is going to be -3/4. That's the power. So then we're going to factor this out. Next step, we're going to factor. What are we going to factor out? We're going to factor out 1/4, right? Why not? You know, 1/2, 1/4, we're going to factor out the largest common denominator. And inside, right, we're going to factor out this piece. Okay, so here, what do we have? We're going to have 2 times x raised to the power of 1/4. Subtracting. This whole thing is being factored out, so we just have 1. All right? And the negative exponents can be written down in the denominator. So this will confirm to us one more time. This will confirm to us one more time that the positive exponent, so this tells us the domain has to be greater than 0 because we have x to the power 3/4 in the denominator. X raised to the power 1/4, that's really x raised to the power of the fourth root. Okay, whichever way you like it to, it's not going to change the results. It's to help you to just help us see better. Okay, so we have a critical number already. So we will have another. We'll have another critical numbers coming up by setting first order derivative equals to 0. So we're going to set the first order derivative equals to 0. Right, so we're going to set first order derivative equals 0, and then the numerator has to be 0. Denominator cannot be 0 for sure, so that would be 0. Okay, so how do we solve this equation? Well, we just add 1 on both sides divided by 2, right? So we add 1 on both sides and divided by 2, so we get 1/2. And then we're doing all of these operations in the domain of the function. So we're gonna, take a power 4 on both sides. So we power 4 on both sides. So now on the left-hand side, we have x, and the right-hand side is 1/16. So we got 2 critical numbers. Oops, sorry. What did I do? Okay. We got critical numbers. And one critical number is 0, and the other critical number is 1/16. And then we're going to choose between, then we're going to have to choose critical derivative tests, right? If we do first derivative test, suppose we do first derivative test. We do first derivative test. If we do first derivative test, knowing that we have 0, 0 is not in the domain of the derivative, right? So we're going to have this number line, and this number is 0, but 0 is not in the domain of first order derivative, but it's a critical number. And the other number is 1/16. Okay, it's 1/16. And so between 0 and 1/16, let's see, is this well, the denominator is positive for sure. The denominator is always positive, right? So the numerator, when x is less than 1/16, right? When x is less than 1/16, what is the sign? What is the sign, right? So here, you can do a little mathematics to do it, right? Because if because we look at the sign of the first order derivative in this interval, and we know here is a 0. We know over here is a 0 because it's a critical number, right? So what is the sign over here? So if we do it mathematically, right? So because in this piece, x is, you can do this. I pretend this is, scratch paper. Okay. So what I'm doing is I'm going to see whether this is a positive. Okay. So x, of course, is larger than 0. So if this is the case, x is less than that. So we're going to replace x by 1/16, right? X replaced by 1/16. 1/16. Okay. So this whole thing is going to be 1/2. 1/2 times 2. 1/2 times 2 is 0. I'm sorry, it's 1. 1 minus 1 is 0. So in this part, it's negative. Okay, it's negative. Negative. You can pick a test number. You can pick a test number. And larger than that, of course, is going to be positive. What does this tell us? This tells us, okay, by first derivative test, f prime changes from negative to positive where? At 1/16. At 1/16. From negative to positive, so we have a local max. I'm sorry, we have a local min has a local min at 1/16. 1/16. And what is the value? Okay, I think I did the calculation a bit earlier. So we're just plugging in to the original function, okay, to the given function. Okay, the given function, which was here, right? We plug it in, this function, we got a root of 1/16, that's 1/4. This is half, so -half. So local minimum point is this piece, okay? So this is the local minimum. Now, about the other critical number. How about the other critical number? For the other critical number, that we understand that from the other critical number from 0, we've been decreasing, right? So 0 must be, f must have a local max. Okay, f has a local max at 0. Okay, simply because we use a derivative test. The other side, there's nothing, right? We don't know anything, so decreasing. So it's kind of first derivative test did not state this situation. So we use so what we analyze is also correct. So we just plug in the value, right? So f of 0, right? F of 0, so this is going to be 0. So this is going to be 0, this is going to be 0, and that's going to be 0. So the local max is going to be 0, 0. Okay, so this is the local max. So this is the first derivative test. It is done. Can we do second derivative test? Okay, obviously, we cannot do second derivative test at 0 because you cannot plug in. But we can do second derivative test for 1/16. Okay, so second derivative test. Oh, sorry, derivative test. Second derivative test cannot be done for 0. Cannot be done for 0. Okay, if you look at second derivative test, you can see, first derivative is not defined as 0, right? But we can do second derivative test. Derivative test for 1/16. Okay, so we can do second derivative test for 1/16. Okay, let's see. We're gonna have to find second derivative, right? So we already have first derivative. Second derivative, which one we're gonna use to find second derivative? Obviously, we're not gonna use these. We probably want to use this one to find second derivative. Okay, we're gonna find second derivative from here. Oops, sorry, x equals 2. So we just continue to use power rule, okay? So for this piece, we have half, and then we're gonna have -half, and x raised to the power of -half minus 1 is -3/2. Minus 1/4 multiply -3/4, right? -3/4, oops, -3/4, and x raised to the power of -3/4 minus 1, and that's going to be -7/4. -7/4. Okay, which is -3/4 minus 1. Okay, just in case. All right, you got it? All right. So this is 7. Now we're going to apply second derivative test for 1/16. Okay, obviously, first derivative at 1/16, that's 0. We know that for sure. Okay, that's equal to 0. Secondly, we're going to test second derivative at 1/16. Boom. What do we get? Well, let's organize this term a little bit. Okay, we have somewhat a mess. We actually don't need to do any factoring, by the way. Okay, you don't need to do any factoring because we're just doing second derivative test. So this whole thing is -1/4. Okay, and this whole thing, that's going to be plus 3/16. 3/16. And then we're going to substitute second derivative, which is this piece, by 1/16. By 1/16. Boom. Okay. We do the same substitution for this other x. Okay, so let's do our calculation. No fear, okay? Keep calm. I know some of you might panic, but there's no reason to. Okay, just follow me with your paper pencil. All right, so -1/4. So what I'm gonna do is I'm gonna copy this and read and do the changes over, okay? So this is actually 2 raised to the power of -4, right? 1/16 is 1/2 to the power 4, because 16, okay? 16 equals to 2 to the power. Okay, you got it? And so this is gonna be 2 to the power of -4 over here as well. Okay? So 16 to the power of, so 1/16. So 1/16 is 2 to the power -4, right? Okay, so we got that. It's just some basic arithmetic. So what do we do now? We're gonna multiply this exponent with this exponent. Okay, so let's do that. Have your paper pencil and just follow me, okay? So -2, so we're gonna multiply these two exponents. Oops, sorry, this needs to be in the power, okay? So that's gonna be -4. So we multiply in the power, -3/2 multiply -4. What do we get? We got, that's negative times negative is positive, right? 3/2 times 4, and that's going to be 6, right? And we do the same, okay, with that. Okay, same thing. And this is going to be negative times negative is a positive, so it's 2 to the power of what? 7. So it's not that scary, isn't it? And then what? Then what? We just need to know whether this is a positive or negative, right? So by this time, I think we're almost there. We're almost there. 2 to the power 6, 2 to the power 7. Okay, so just be patient with me and take this as an opportunity to improve. So 2 to the power 6 can be written as 2 to the power 4 times 2 to the power 2, right? 2 to the power 2 is 4, so that reduces 1/4. So that's going to make it, this whole thing is going to be, make it like just -2 to the power 4. And this piece, 2 to the power 7, can be written as 2 to the power 4 times 2 to the power of 3. So just split it. So 2 to the power 4 is 16, and 16 and 16 reduced, right? So this piece will just be have 3 times 2 to the power 3. We're almost there. We're almost there. Can we determine if this is a positive or negative? Just one more thing. -2 to the power 4, this is -16, plus 3 times 8. 2 to the power 3 is 2 times 2 times 2 times 2, 3 times. And 3 times 8 is 24. So this product is a positive. All right, so by second derivative test, it's greater than 0. By second derivative test, this is a concave up at that, at the critical number. Okay, concave up. So F has what? Local minimum at 1/16. At 1/16. Okay, is that the same conclusion we drew earlier? Local minimum? Yes, local minimum. So the rest is just, we're gonna plug in the same thing as we did earlier. Local minimum. For 0, however, we cannot do second derivative test in this case. Okay, so we drew the same conclusion. Last but not least, Okay, last but not least. Okay, so this piece of note, I'm still gonna keep it here. So this question is pretty much done. I try to get a nice picture for all of us. Actually, I got one. It's not ideal. Yeah, I also found the work I did earlier. But anyway, so this piece, this is the curve. This is actually the curve. So you can see we have a local max here, which is 0, 0. There's local max there. Okay, so local max there, local minimum. Okay, this is probably also a absolute minimum. But this picture just is not as good as I wished. Okay, so I saw this picture, and I'm gonna screenshot and bring it back here. Okay, so this other picture, hold on. So 0, 0. Okay, and so I'm gonna bring you another picture. Just hold on. Okay, hold on. Just 1 second. All right, I'm going to bring the other picture back to our picture. And this other picture, I did it from the other software Desmos. Okay. So you can see that's what we got, right? We got it right. Okay, this is the lowest point. That's the locally highest point, because this curve will keep going up. This is just a local max, local min. Okay. The third example, someone asked this question, so I thought, hey, why not, right? So let's just finish it. We're gonna bring this back. I tried to cut down the amount of time we're gonna spend here. First order derivative. Okay, so these are the work we're done. So finally, the first order derivative is here. We don't need the other stuff. Okay, first order derivative. In terms of domain, right? Domain of the function from the beginning is all real numbers. All real numbers. All real numbers. And this domain, however, domain of the derivative, that x cannot be 0. X cannot be 0. This makes 0 a critical number. Okay, so we already have a critical number 0. And if we set the first order derivative equals to 0, okay, we set the first order derivative equals to 0, right? We set it equal to 0. This x plus 1 will have to be 0, right? So x plus 1 will have to be 0. So x equals to -1. So our critical numbers are 0, 1. Or -1, sorry. 0, -1. All right. All right. So next, derivative test. Derivative test. Okay. Derivative test. First derivative test. Okay. Remember here it's just looking for max, min. We're not talking about increasing, decreasing. So we don't need to give those intervals. All right. Then you say, well, if on the test I give you extra, do I get extra points? No, I don't think so. Okay, because we have to keep the amount of time we have for the quiz under control. Okay, it has to be in some kind of control. Okay. All right. So just get there straight. First derivative test. So we have two critical numbers. And we're gonna have to, we're gonna have to figure out the sign of the derivative, right? So this is pretty straightforward. However, okay, we are taking cubic roots. We're taking cubic roots. So we're gonna rewrite this in a form which is more familiar to us. This is a positive 2/3. That's in the denominator. And if you like, we're gonna write it in the root form. So if that makes it easier for us to see. Okay, so now you can see the denominator actually is always positive, isn't it? So the sign of x plus 1 is going to be the sign for the entire derivative. Okay, the sign of x plus 1 is going to be the sign for the entire derivative. All right, so let's look at the sign. The sign, this time we don't need to put it in pieces, right? We can just work with it. We have two numbers. One is 0, critical number, and the other critical number is, oh, put 0 here, -1 here, I'm sorry. -1, okay? Okay. We basically have three intervals. When x is less than -1, when x is less than -1, denominator is always positive. Okay, 4/3 is positive for sure. And when x is less than -1, so this piece is going to be, derivative will be negative. At -1, it's 0. And more than -1, right? That's going to be positive. How about in the neighborhood of 0? At 0, we cannot. This is undefined, okay? So we're not going to put anything here. And how about when x is greater than 0? When x is greater than 0, it's also positive. You can see that? Can we see that? Okay. First derivative test. What do we see here? Right? At 0, above -1, we're, so we got a decreasing, increasing. We got the local minimum. But at 0 to the left and to the right, the derivatives are positive without change. So is 0 a local max or local min? It's neither. Okay? So take a second look of this first derivative test, please. Please take a second look of the first derivative test. This case is the third category. Okay, it's the third category. Hold on, I need to get my glasses. Hold on, I'm gonna pause. Okay. Heck is the first derivative test, right? So let's make the statement. First derivative, right? We're talking about the critical numbers. The first derivative changes from negative, got my glasses, from negative to positive. Okay, where? At -1. At -1. So the function c of x has a local minimum at -1. Has a local minimum at -1. Okay, and the value of the function at -1, we're going to plug in, right? We're going to plug in the original function c here is going to be -1, and over here is going to be -1, and that's going to be -1. -1 raised to the power of 1/3, that's the cubic root, that's going to be -1. And -1 times +4, that's equals to 3. So equals to -3. So that's a local minimum. And C, first derivative changes from positive to positive at 0. According to first derivative test, C, the function has neither local max nor local min. Okay, at 0. That's it. Okay, it has neither. It has neither. Okay, we can do the graph to verify that. To verify that. But we're gonna do second derivative test. Okay, so let's do second derivative test. Second derivative test. Obviously, we cannot do second derivative test at a critical number 0. We can do second derivative test at a -1, right? So we're going to copy and paste all of these work. Critical, up to critical numbers. Okay, for second derivative test. And then we're going to find second order derivative. Second order derivative is the derivative of the first order derivative. So which one we're going to take first order derivative? I'm sorry, which first order derivative we're going to take, right? So we're going to have to pick and choose. We're going to have to pick and choose. Which one do we want to use, right? We can use this one. We're going to have to use the product rule anyway. We're going to have to use the product rule anyway. So how about we just use this one? Okay, let's take a derivative on this one. All right, so we're going to take a derivative on this piece. All right. To do this, I like to keep things simple. Okay, I'm going to bring this one outside. Okay, so in my derivative taking, I'm not going to deal with that number. So I'm just going to take derivative of this piece. Product rule. Product rule. Okay. So for thirds, it's going to be outside brackets. In the bracket, we're going to do product rule. Okay. So it's -2/3 x raised to the power of -2/3 minus 1 multiply x plus 1. Okay, plus, and I'm going to keep the x raised to the power -2/3 and differentiating the next one. So this is just the derivative of this piece, x plus 1 is just 1. Right? So we're done. Okay? So we're done with the derivative part. The question is, okay, let's just simplify this. This is just going to be -5/3. And this just be simplify it, right? Is there anything else we can do? I think no. That's it. That's it. The question is, do we need to factor and simplify for second derivative test? The answer is no. We don't need to do more work. Okay, we don't need to do more work. Because we already know first derivative at -1 is 0. Right now, look at your second derivative test. We still have to evaluate second derivative at the point -1. So we just need to work on this piece. Okay, at -1. So we're gonna bring this x, replace x by -1. And this is -1. And this piece is -1. I think you probably already see some convenience, right? This piece is 0, right? 0 times all of that is 0. Okay, so let me show you. -1 plus 1 is 0. 0 times anything is 0. So that's 0. And what is this? What is this? Okay, be careful. Okay, you need to know how to evaluate this. This is basically a cubic root. Okay, but you're going to change it to be, because it's a negative exponent. It's a negative exponent. Okay, so it's a root 3. It's a cubic root and squared. All right, so this number, be careful, this number is -1 raised to the power of +2/3 under 1. And this -1 is being squared. So this piece is a positive. Okay, it's not negative. So this piece is a positive, positive times positive, this is a positive. That's all we need to know. Okay, so we have second derivative at -1 is greater than 0. Now we draw the same conclusion. We really draw the same conclusion that it has a local minimum. Okay, has a local minimum. Okay, same conclusion. All right. And how about the other critical number? The other critical number we cannot. Well, we have to use first derivative test to test it, and we already tested. Okay, so that is all for these examples. All right. Let's see how much time we have. Okay, so let's close this. If I record, I'll record another one, but let's not make this too long. Thank you for watching.